Hello everyone, we're going to do presentation on beam column. Let's start. First, what is a beam column? It is a structure members that is subjected to both bending and compression. This is known as the beam column. Bending may be caused by moments applied at ends of the member and the transverse load acting directly on the member. The analysis involves the feature of both the deflection problem as a beam and stability problem as a column. So, as a beam problem, the bending moments induced in a member by the application of end moments or by span transverse loading, so by combination of both. As a column problem, the axial force at certain critical values will cause instability of the member. Now, if we take in a case of beam columns, the axial force will act through the lateral deflection caused by the bending effect. That will produce an additional lateral deflection and moment in the member. This additional moment and the lateral deflection is referred to as secondary moment and deflection. The secondary deflection of a beam column caused by the axial force effect is sometimes more significant than that caused by the primary bending effect. Vertical members in rigid frames that are both bent and compressed are beam columns. Beams and columns are regarded as special cases of beam columns. Now we'll go for beam column with concentrated lateral load. First of all, let us consider a simply supported member of length L, which is simultaneously acted on by a transverse load Q and axial force P as from this figure. The assumptions we make in this derivation are the materials behave according to Hooke's law, deformations remain small, the member is laterally braced so that it can only bend in the vertical plane. Now this critical derivation, the external moment at a distance x from the origin is given by the equation m is equal to qx by 2 plus vy. Equating this expression to the internal resisting moment, that is minus e by y by double dash gives the following equation. Assuming k squared is equal to p by ei, the general solution to equate the first equation is y is equal to a sin kx plus b cos kx minus qx by 2p. Now applying the boundary conditions there, that is y equal to 0 at x equal to 0 and b equal to 0, we get dy by dx equal to 0. At x equal by 2, we get a is equal to q by 2kp into 1 by cos kl by 2. Substituting of these results in the equation 3 gives y equal to q by 2pk into sin kx by cos kl by 2 minus kx. To find the midspan deflection, we assume x equal to L by 2 in the equation 4 and we obtain the deflection equation. Multiplying and dividing this expression by L cube by 24 ei, we get the expression for the midspan deflection, that is delta. Now let's introduce the notation delta 0 is equal to q L cube by 48 ei and rewriting this equation as delta is equal to delta 0 into delta 0 cube into tan u minus u by u cube. Substitution of this series for tan u in the equation 9 gives delta is delta square into 1 plus 2 by 5 u square plus 17 by 105 u raised to 4, etc. U square is equal to p by ei into L square by 4 pi square by pi square. That is equal to 2.46 p by PCR. PCR is the critical Euler law. And this equation can be rewritten as delta 0 into 1 plus 0.984 p by PCR plus 0.998 p by PCR square, etc. Since the sum of the geometric series in the bracket is 1 by 1 minus p by PCR, this equation reduces to delta 0 into 1 by 1 minus p by PCR. The conclusions we get from these equations are that this equation indicates the maximum deflection of the number is equal to delta 0, the maximum deflection that would exist if only q were acting multiplied by an amplification factor that depends on the ratio p by PCR. The equation shows that the deflection of the beam column increases without bound as p by PCR approaches unity. It is thus possible to determine the critical load of a number by finding the axial load at which its bending stiffness vanishes. The maximum bending moment is equation, and maximum bending moment is given by the equations m max is equal to ql by 4 into 1 plus Pm square by 12 EI into 1 by 1 minus P by PCR. This can be simplified to Mmax is equal to QL by 4 into 1 plus 0.82 P by PCR into 1 by 1 minus P by PCR. The maximum moment in P4 can be given as Mmax is equal to M0 into 1 minus 0.18 P by PCR divided by 1 minus P by PCR. Now we will see P4 distributed lateral load.
Beam column with distributed lateral load. Consider the case of a simply supported member when by a uniformly distributed lateral load W and a set of axial force P, as shown in the figure. By Rayleigh-Ritz method, the analysis of a beam column by the energy method is similar to the analysis of an axially loaded member. That is, the energy of axial compression is omitted and only bending energy is considered. The strain energy that is stored in the member as it bends is U is equal to EI by 2 integral 0 to L d square y by dx square whole square into dx. The potential energy of the external load is V is equal to minus W integral 0 to L y dx minus P by 2 integral 0 to L dy by dx the whole square dx. The total energy in the system is U plus V. Adding the upper two equations, we get this equation EI by 2 integral 0 to L d square y by dx square the whole square into dx minus W integral 0 to L y dx minus P by 2 integral 0 to 1 dy by dx the whole square dx. To satisfy the boundary condition, the deflection y is assumed to be of the form y is equal to delta sine pi x by n, where delta is the midspan deflection. Substitution of this expression into the initial equation will give us the below equation U plus V is equal to EI delta square pi raised to 4 by 2 L raised to 4 integral 0 to L sine square pi x by L dx minus W delta integral 0 to L sine pi x by L dx minus P delta square pi square by 2L square integral 0 to L cos square pi x by L dx. To evaluate equation 3, we make use of the following definite interval. Integral 0 to L sine square pi x by dx is equal to integral 0 to L cos square pi x by L dx is equal to L by 2. Integral 0 to L sine pi x by L dx is equal to 2L by 5. Thus, equation 3 becomes U plus V is equal to EI by delta square pi raised to 4 by L cube minus 2W delta L by 5 minus P delta square pi square by 4L. For the system to be in equilibrium, the derivative of U plus V with respect to delta must vanish. Thus, dou U plus V by dou delta is equal to EI delta pi raised to 4 by 2L cube minus 2WL by 5 minus P delta pi square by 2L is equal to 0. Delta is equal to 4WL raised to 4 by 5 L into L by EI pi raised to 4 minus P pi square L. If the numerator and denominator of the above equation are multiplied by 5 by 384 EI, the equation becomes, on rearranging, delta is equal to 5WL raised to 4 by 384 EI into 1 by L minus P by P CR. The left-hand factor in this relation is the deflection that would exist if the lateral load W was acting by itself. Thus, let delta 0 is equal to 5WL raised to 4 380 EI. Then the equation becomes delta is equal to delta 0 into 1 by L minus P by PCR. Equation 8 gives the maximum deflection of a simply supported beam that is bent simultaneously by a distributed transverse load W and axial force P. The maximum moment in the member is given by Mmax equal to WL square by 8 plus P delta. Mmax is equal, on substituting the other equation, Mmax is equal to WL square by 8 into 1 plus 5PL square by 48 E into 1 L by L minus P by PCR. Simplifying the terms inside the bracket, one will obtain Mmax is equal to WL square by 8 into 1 plus L plus 0.03 P by PCR by L minus P by PCR. The term outside the bracket is the maximum moment that would exist if no axial force were present. So 0, let m naught is equal to w square by e. Then the equation can be rewritten as m max is equal to n0 into L plus 0.03 P by PCR by L minus P by PCR.
Coming to the failures of beam column, failure usually occurs by yielding. It becomes necessary to introduce the complexity of inelastic behaviors into the investigation. Inelastic bending do not possess closed form solution. They must either be solved numerically, which entails lengthy and time-consuming calculations, or approximate answers must be sought out by making simple assumptions. And these assumptions include: 1. To obtain closed form solution of the load deflecting characteristics beyond the proportionality limit, forming assumptions are introduced. The cross-section of the members is rectangular. The material is an ideal elastic plastic material. The bending deflection of the member takes form of a half sine wave. In addition to this major idealization, the following assumptions are made. Deformations are finite but still small enough so that the curvature can be approximated by the second derivative. The member is initially straight. The bending takes place about the major principal axis. The following shows the derivation of simply supported symmetrical loaded member. As shown in the figure, the member is simultaneously bent and compressed by equal n couples M and axial forces P, as shown in the figure. The external bending moment at a distance x from the origin. Moment external is equal to m plus py, and the internal moment is given by minus ei del y square by del x square. To determine the relation between load and deflection up to the proportional limit, we equate 1 and 2, and we get equation p plus m plus py is equal to minus ei del y square by del x square. If the deflection is now assumed to be of the form y is equal to del sine phi x by L, the curvature can be written as del square y by del x square is equal to minus del phi square by L square sine phi x by L. Substituting the above equation, we get m plus py is equal to e by I del phi square by L square sine phi x by L, which can be reduced to m plus p del is equal to ei del phi square by L square at the mid-expanse, assuming that m is proportional to p, and we introduce the notation e is equal to m by p, and rewrite the equation 6, and we get e bracket e plus del is equal to del pe, where pe is equal to phi square ei by L square, which is the Euler's load of the member. If both sides of the equation 7 is divided by the depth h, and rearrange, we obtain the equation del by h is equal to e by h into 1 by del e1 by sigma e by sigma naught minus 1, where sigma e is equal to e divided by b into h, which is the Euler stress, and del naught and sigma naught, which is equal to p by b by h, which is the average stress. To determine the load at which the equation 8 becomes invalid, one must first consider the maximum stress of the member. And therefore, we get the equation sigma max is equal to p by breadth into height plus m plus b into del divided by b breadth into height square divided by 6. Substituting the values of pe for m and sigma naught for p by a p divided by breadth into height, we get the equation sigma max is equal to sigma naught into 1 plus 6 into e plus del divided by h. The elastic load deflection relation given by equation 8 becomes invalid when sigma max is given by equation 10 equals to the yield stress. The inelastic moment curvature relation that must be used in place of equation 2 once the stress has been exceeded the proportional limit, and we get the equation y double dash is equal to 2 sigma naught h into sigma y by sigma naught minus 1 whole cube divided by 9 into e h by 2 into sigma y divided by sigma naught minus 1 minus moment in internal moment divided by the whole square. The curvature and the moment at mixed lengths are given by y double dash into del pi square by L square, and the moment internal moment is equal to internal moment at the mixed length is equal to P into E plus del x E plus delta. The substitution of this experiment into the substitution of these experiments into uh, can be expressed into del by h del by h into half into del y plus del y minus sigma y minus sigma naught minus 1 minus e by h minus delta by h whole square, which is equal to 2l square sigma naught divided by e into pi square into h square, which is into uh, sigma y minus sigma naught minus 1 to the power cube. Since the inlet stress can be expressed as sigma E is equal to pi square EI divided by AL square, which is equal to pi square E into H square divided by 12L square. The equation 12 can also be written as del divided by H into half into sigma Y minus sigma naught minus 1 minus sigma minus del by divided by H minus E divided by H to the power whole square. And which is equal to 1 by 34 into 1 divided by 34 into sigma naught divided by sigma E, which is A into, which is then multiplied to sigma Y divided by sigma naught minus 1 to the power cube. The above equation 14 it gives the load deflection relation of the inelastic range. It can be used from the onset of yield up to the failure, provided failure occurs before yielding commence on the convex side of the member, which aids to the equation 4 and equation 14 given above.